Hey everyone, welcome back to the channel. Today we're going to do a quick start guide into LLDB. This is going to be a tutorial video on working with LLDB directly from the terminal. I'm not going to go over how to install it because this video would get far too long. I would recommend looking up how to install LLDB or LLVM, the entire suite of tools for your particular operating system or Linux package manager and whatnot. But this tutorial will focus on using it, setting breakpoints, watchpoints, navigating around, inspecting things, that sort of thing. So without further ado, let's dive right into it. So LLDB is a standalone debugger that you would run from the terminal and you would attach it to your executables and then set some breakpoints and navigate and inspect and whatnot. Most C++ IDEs or editors will have their own integration with a debugger. Visual Studio uses Microsoft Debugger. Xcode will use LLDB directly. Other tools will use GDB, which is another standalone debugger. They usually have different modes for integrating with IDEs and stuff like that. But what we're going to look at today is actually using it directly and getting ourselves familiar with the various commands that you would use to attach to an executable and to set breakpoints and to inspect variables and all that stuff. So let's take a look. The first thing we need is a program to debug. So I've written this short C++ program that doesn't serve any purpose whatsoever other than to demonstrate the various features of LLDB that we'll be going over. So don't look for any reason for why any of the stuff happens, why any assignments or function calls exist. This is just for demonstration purposes. So let's actually switch over to the terminal and I'll show you how to compile for debug. So if you're compiling your code directly with the compiler like this, what you want to add is -g and then your compilation unit, which in our case is demo.cpp. And when I hit enter, GCC will compile this with debug symbols enabled. If you're using Clang, it's the exact same command, and that will now compile it with debug enabled. If you're using CMake, I recommend you take a look at this variable that needs to be set in your build in order for you to turn on debug builds. What you do is you set this to either debug or, so actually I'll show you real quick. If you're running CMake, you would essentially pass this in and you'll say CMake build type equals debug, and then your CMake list file. And when you pass this variable in and set it to debug, then what CMake will do is it'll make sure that your compiler is called with whatever flags in order to compile it with debug symbols enabled. I'm not going to spend too much time on that, but just know that you have to enable the debug symbols in order for LLDB to be able to pick up your source code and know variable names, and to just be able to provide you source code information as you're navigating around and setting breakpoints and all that kind of stuff. So the first thing we got to do is we got to actually start LLDB and tell it what program to run. So by running LLDB and passing in the name of our program as an argument here, then LLDB will run and create a target that it's then going to execute and attach to whenever we actually run the program. If your program has arguments, this is worth noting, you would pass those in. So if you have to type something after your program, like I don't know, a folder name or something, right? If your program accepts command line parameters, then you would essentially pass those in this way. So you do -- space the name of your program and then whatever arguments afterwards. And if you want to actually set those from within LLDB, there's a much more complicated and annoying to type version, which I don't know why anybody would do this, but you can do that right from within LLDB this way. And in fact, if you actually run this command, LLDB will actually show you that this is the command that you can run from inside of LLDB to do the exact same thing. I'm not going to spend too much time on that. It's this, to me, I don't know why anybody would prefer this over just doing that. But this is how you specify those parameters. And then we're going to run our actual executable from within LLDB by using the run command, or just R for short. So let's run LLDB. We're going to pass a.out. And now, as you can see, we've started LLDB, and like I said, it creates its own little target so that it can run our program, and it sets the executable to our actual executable here. The other way to do it is to just run LLDB, and then you can do file a.out. So when you run LLDB, you're in the current folder, and that's where it'll look for files. So you can do file space, you can do, you know, if you really wanted to, you can do // to go one folder up or whatever. But in our case, we're just gonna tell it to use the current directory, a.out, and it does the exact same thing. And now if we do run or just R, it runs the application. The other thing that I was showing earlier is that what this program does is if you pass a parameter, it checks if you've passed the parameter, and then it just prints it back out. I did it just for testing. So if I do a.out hello, then the first thing it does is it checks if I typed in anything after a.out, and then it just prints it back out, right? That's what the if is here. So this is what I did. If I don't put anything, then obviously it won't echo it back out. Now, if you wanted LLDB to use that parameter every time it runs, you would do this a.out and then hello. So it's the exact same thing you would type in the terminal, except you need to pass it in this way into LLDB. So when I do that, we start LLDB, it sets the actual parameter using this argument, and then when I run it, you'll see that it now ran it as if I typed hello after my executable. This is very useful depending on what kind of utilities you're working with, and you don't want to keep typing certain arguments or whatever. You just specify those when you launch LLDB, and then you can use the same test data or same arguments every time you run your executable. So obviously the next thing we want to do is we want to actually set a breakpoint and be able to stop somewhere and take a look at certain things. So I'll quickly show you how to set breakpoints. One thing to keep in mind is that there's a shorthand for that as well, and I'll show you how this works. But the main command, if you want to just know exactly what it does, break is the breakpoint command, set, so we're setting a breakpoint, and then we could do -f to specify the file, and -l for the line number inside that file. So if we actually look at our code and we say let's set a breakpoint on line 36, what we would do is then go inside LLDB, we'll say break set -f, and know that you could actually do tab completion here. So I'll type just demo, and then it'll pick up that I have that file on my project. Oftentimes it'll actually suggest all kinds of other stuff that might be picked up from like the runtime library and other operating system things that are loaded when you actually attach to an executable. So you know, if I do just DE, then you'll see there's all this other stuff that it might suggest. These are things that are pulled in because the application requires certain libraries and certain facilities to be loaded in order for the application to actually operate. But we're going to type just demo -l, and then we said we want it line 36, and we're going to set a breakpoint at line 36. Now when I run the application, there it is. We have our debug information loaded, so it knows the actual code that it's stopping at. Line 36 is exactly what we just looked at here. We want it to break here, and yeah, and our breakpoint works. If I exit, and then actually let's go back in, and then I'll show you. You can do br set, the exact same thing, demo, and then -l. And this will set it the exact same way, but the way I prefer to use is just B. B will set a breakpoint, and here it's actually a lot easier to, you don't have to do -f -l, you can just do demo.cpp and then colon the line number, and then this does the exact same thing, and it's a lot more straightforward. So this is just, I find this to be the quickest way to just, if I want to debug something, I'll just hop in B space the file name and the line number, and then it just sets it. The other thing you got to note is that you don't need to use just line numbers. You can actually put breakpoints on symbols, so you can put it on a function. So we have a function called square, and every time that function gets called, I want a breakpoint. So if I want to set that, I can say it'll pick it up as a symbol, and it knows that this function here, because it has all the debug information, it knows that this function exists. So when I do, like I just did sq, bsq, and do tab, it'll complete it for me. It'll know that I have this function in my program. And if I do that, now anytime that function gets called, it'll break. So if I run again, Obviously we haven't called it yet, but that function gets called, where is it? It gets called right here, right? We're actually right at line 37. So if I go continue, it'll actually break inside the function, as you can see right here, and it'll break on the first line of that function. So let's continue again, and then it gets called again, and then the program terminates. You could also put it on a class. So if you have a class with a method, for example, in our program, we have this class right here called demo. It's very simple. It doesn't do anything, but it's a struct or class, doesn't matter. But I use the struct just so everything's public by default. But we have a struct called demo, which has this member variable, and a function or a member method called demo. And now if we want to break every time this function gets called, we could just go here and do, what was the command? It was b demo, and then because it only has one function, it just completes that one function. If we had multiple functions, then it would stop here and allow us to start typing our function name. But because demo only has one member that you could actually put a breakpoint in, I'll hit enter, and then we have a breakpoint there as well. And if you have a namespace, you have to take that into account, because if you're just, for example, let's go here and take a look at this function. We have this add function here, and if we wanted to break inside this function, then if I just start typing b add, it's not gonna find it. It's gonna show me all this other stuff, and I'll be like, why can't I break on that? It's because you have to factor in that it's inside of a namespace. So if I go b LLDB demo, again, it's the only function that's in there, so it's gonna automatically complete that function. But you have to use the same format to actually specify the namespace that the function is in order to actually be able to find it. And then if I do that, as you can see, we have another breakpoint. So now we have 4 breakpoints, which leads us to our next point, which is manipulating them. So if you wanted to actually list your breakpoints, you can do br list, or just break list will give you all the breakpoints. But again, br list does the same thing. It's more shorthand. And this shows us, we have on line 36, which was our first breakpoint. Then we have square, which was our second one, the one that we set on the class, and then the one that we set on the namespace function. Now, I want to reset this. And the way you do that, if you want to actually delete a specific one, I'll show you how to do that. But I'm going to want to delete all of these breakpoints. But let's actually delete that for the fourth one first. So the way you do that is br del 4, and then it just deletes the breakpoints. And now if we do br list, we'll see that's gone. But I kind of want to just clear them all so that we can do some other demo stuff. If I do br del, it says about to delete them all. Yes, gone. And now br list, we have no breakpoints. And that's it. The next thing we want to do is we want to be able to navigate around our code and jump in and out of functions and actually run the program line by line so we can issue debug commands. So I'll quickly show how to navigate inside the program, and then we'll move on from there. So if I run it, right, we have no breakpoints right now. What I'm going to do is I'm going to set a breakpoint on main, which you can do this, and it'll put the breakpoint right on the main function, which means as soon as the program starts, it'll halt. So if I do that, it says line 31 inside demo CPP, it found main, and that's the first executable line of code inside main.cpp. So I told it to break on main, and then what the debugger does is it goes, well, this is not a line of code, this is just scope information, but this is a line of code. So then this is where it puts the first breakpoint. And now if I run this application, as you can see, it goes to that line 31 and it stops. Okay, so if I wanted to just go to the next line, I can do n, right? Step over means to go to the next line, n. If I wanted to continue navigating, I'm having some trouble with Alt Tab here, I can do n again. And now notice it's skipping over these, right? These aren't lines of code. This is just source code information. These are instructions of code, right? Now we're in this line here. We can continue, go next. And now let's say we want to inspect what happens inside square. What you do here is you step into it. So what we've been doing is stepping over. That's what next means. Generally inside a IDE or an editor, if you have that button to navigate with the debugger, it's actually called step over or step into. That's usually what these things are called. So what we want to do here is we'll say, okay, well, I want to actually see what happens inside this function without actually setting a breakpoint. So what I do is I type S, which is short for step into. And now it's stepped into the function in here. If you have multiple functions, it's going to step inside each ones as they're evaluated. There's an order that things are evaluated in these languages, and it's if I had square times square and I'm calling square twice, it's going to step into it first here and then it's going to step into it again. But anyway, so I've stepped into this function, and I can't. If I do S again, there's nothing for it to step into, right? Like this isn't a function, this isn't a function. It's nothing callable. So if I do S again, it's going to do the same thing as just doing N. And now if I go next, it goes over to the next line. If I do S in here, it's not going to actually step into anything, even though the cout is here. So it knows that I probably don't want to step into standard library stuff, so it kind of just steps over it. In here I can do the same thing. I can do S, or I can actually, look, I can just do N and it'll go right past it. But then I go, oh, I want to step into square again. I can do that. So I think you get the gist of it. It's pretty straightforward. And then I can just continue navigating. And then at the end, when I'm like, you know, I just want my program to just continue running, you can do C, which is continue, short for continue, but C for short, and then just let the program resume. The next thing you're going to want to do is inspect some variables. So you could navigate around your code and sort of follow the logic of your program, but it's often very useful to inspect variables or arrays or anything of that sort, any structures. You can even inspect your objects. So the way you do that is using the print command, which also uses a P for short. And I'll show you how that works real quick. We'll go back to the application and run it. And now we're inside of, we've hit our breakpoint that we had set on main. So let's just step forward a little bit, a couple of lines, and we're now at line 36 again. We haven't run line 36 yet, right? We're currently sitting there waiting. And if I do print value, you'll see that it's going to show a 0 because we haven't actually initialized it yet. If I do next and step over that, and then now this line has executed and we're waiting to execute this one. So because this line has now executed, if I do print value, you'll see that now there's a 5 where before there was a 0. And that's pretty, that's pretty obvious. It's what you would expect. We're now sitting at this line of code here, which is about to call the function square. So instead of stepping over that line, let's step into it. And as you can see, we're now at line 18, which is where this the first executable line of code inside this function. And we now have a function that takes one parameter called a and returns a squared. So there's this concept of a frame. So every time you call a function, there's some information that needs to be retained, telling your application where it needs to go back to once that function executes. So every time you call a function, you have this call stack, functions calling other functions, and they kind of stack on top of each other. And as functions return, this frame of information gets popped off of the stack, and then you always go back to where the function was called. I assume everybody knows that, but oftentimes when you're navigating your breakpoints or you find a crash or something, you're going to want to see what called what and what data was passed in. So you're going to want to inspect the frame for that particular call site or the function that it actually called. So in this case, we're inside frame 0. Because we're at the latest point of execution. We're at the current point of execution rather. And that's now at the top of the stack, frame 0, right? Before we're here, and that was frame 0. That was the old frame 0. But now that we call square, that call goes on the top of the stack, and now we're inspecting that, and now it has become frame 0. So if I do frame variable, right? This will give me the variables inside this frame. Because we only have one local variable, and that's this parameter here, that's all it's showing. If I now go next, and now that call has popped off, right? we're no longer inside here. We have popped off the stack, and now this has become frame 0 again, which is the top of the stack, right? It grows downwards. You got frame 0, 1, 2, 3, blah blah blah, and then they keep popping off, and then the previous thing that was at the top is now gone, and then the thing that was second is now the top of the stack. This stacks are a completely separate topic, but just so you understand. So now we've popped that function call off the stack, and now we're getting the result from square and putting it inside result 1. So let's actually run that assignment operation, and now we've stepped over that line of code. It's run. So first we stepped into this, we got the value, and now we're sitting there waiting for this part of the instruction to run, the assignment itself. Then we hit N, and now we're at line 38 after it has run, and then we can actually print the result, or the value of result 1, which is a 25. That's because we got the square of 5, right? We assigned 5 to value, then we called square, and we got the value of that. Now, sometimes there's so much information on the screen that you tend to get a little bit lost, and you just kind of want to see, you know, like if I hit tab and blah blah blah, all this stuff starts appearing on the screen. Now I've sort of lost where I'm at. Just know that you can always type frame select or FRS and frame select like this, kind of like I showed here, or FRS, and it shows you can always go back and see where exactly you are in the current frame. So the next thing I want to explain is knowing how to work with the backtrace and the various frames that are present during the execution of your program. If there's a crash or if you hit a breakpoint, you're going to want to see what was actually going on. So we now know how to inspect the frame. We know how to print out the contents of variables and things like that. But maybe we're interested in more than just the current frame, the current call, or the current function that we're currently inside of. So let's go back to the code and then put a breakpoint inside main again and run our program. So we're back in here. We're inside frame 0, right? So one thing I want to show you is I'll run BT, which stands for backtrace, right? It's tracing back the call stack. So when we look here, we'll see that we're inside main, right? That's the first function. So this is the start of our program. This other stuff here is usually OS related stuff or debugger related stuff. So I'm not really interested in this. What I'm interested in is this function call right here, main. So main is the function that gets called when your program starts, and this is the frame that we're now at the top of the call stack, and this is what we're interested in. So if I continue here, now we're at line 37, which calls square. So when we call square, we're going to actually put another frame on the stack, which is essentially going to keep, it's going to have some information about how to behave after we finish executing square. So once square returns, let's step into it actually. So once this function executes, or once this statement here rather executes, and we return out of square, we're then going to be back here. So the frame, like I said, includes information that we need to go back to line 37. It's stored differently than that. It doesn't track line numbers, but it knows that we need to return back to this line of execution here and continue after square has finished executing. So now that we're in here, we're inside of the square, we're at frame 0, so we're at the top of the stack, right? Because now we've called square and we've pushed another thing at the top of the stack. So if we do BT, you'll see that we have main, and we also have now another frame on top of it, right? This stack, you'll see like the most current, or the most recent call, or the function that we're currently inside of is always going to be at the top of the stack. So now that's what we're seeing here. We're seeing squares at the top of the stack, and it's showing us the various parameters and their arguments that were provided. So we can see that we're now inside square, and we can do FRV and actually print the value of the variables inside this frame. If I now step over that and I go back to the call site that actually called square, if I do BT, we'll see that that frame has popped off and we're back to main. We're back inside main. So that's pretty useful, right? But now let's actually continue executing. And now we see we're about to call this function here, demo. So let's step inside of it and do backtrace again. Well, there it is again, right? We're now inside of demo, so we have another frame of information on top, and we can see that main called it, right? But what if we don't want to continue executing? What if we want to actually inspect what was going on in the scope outside of this call? So we want to actually go back to this frame and inspect the variables, because here, you know, we're calling this function here, and we're not seeing any variables. So we're like, okay, well, let's actually hop up one frame and inspect. The way you do that is by, like I've listed out here, is you use the frame select function. So 0 I'm just using as an example here, but you would specify the frame number, or you can just put F for short. Like I said, these shorthands are much more straightforward and user-friendly than typing this all the time. But if we do frame select and we type 1, we're now back at line 41. We haven't run this code yet, right? Like, this is still sitting there waiting. We're still at this point. We've just halted, but we can go back and inspect every frame of execution. And now we're over here, and we can actually inspect the variables inside this frame, right? We can do FRV and inspect those variables, and we'll see all the variables and local variables that were present inside of main when we called demo. Now, like I said, there's, you know, these are not initialized, so they're just showing junk data. But you know, you have to be cognizant of that, because you know, you don't want to think that these are actually initialized and make judgments based on that. So let's actually do BT again and see where what we're currently looking at. We're looking at frame 1. Let's actually go back to frame 0, so F space 0 for short. And now we're back to the current point of execution, and we can actually step over that and continue going forward, right? Now we're out of that, and we continue our execution inside main. That's really all it is when it comes to the backtrace. The other thing I want to show you, I've put this intentional crash in here. I'm dividing by 0, which is not allowed, and I want to halt the program. And I'll show you how that works actually. So let's recompile it. We'll see even the compiler is warning us that we have a division by 0, because these are obviously just hard coded in, so the compiler is able to see, hey, you're asking me to divide by 0 here, and it's catching a silly error for us. But let's ignore that and just run the program. You'll see that we have a core dump. We have an actual exception that's thrown, and the program crashes. So if we want to inspect that crash, let's run our program inside of LLDB and then hit run. Boom, right? Now, instead of just seeing this exception here, we're now seeing an actual crash. We're seeing an integer divide by 0. LLDB is telling us exactly what thread and what frame the crash happened at, and what line number even, right? Line 17. And you're able to see, oh, silly me, there was a crash there. Obviously, if we're just looking at this, we're like, what the hell happened, right? I don't know what this crash is, but when you run it inside of LLDB, and if you have debug symbols enabled, you can now actually see what point of execution caused that crash. Now, usually in order to debug a crash, you're going to want to see more than this, right? We're inside of a square function, that's great, but maybe something led up to that. So let's do the backtrace again, and now we can start to inspect the whole program and how it executed. We can say F1, right? Let's jump into main. Okay, what was going on inside of main before square was called that led up to that? And you can start to inspect some of the variables. Obviously, this error isn't, or this crash here isn't dependent on any of the variables. I just used the divide by 0 so I can trigger a crash. But maybe sometimes, you know, what you passed into square is dependent on what was going on inside the function that called square. So you want to be able to hop around between these frames and inspect things and be able to actually see what was going on and what the call stack looked like that led up to that crash. And BT is the way you do that. It's very simple. And we can also do FRS and actually go back to the current point of execution if you ever get lost, the current point of execution of the current frame. But let's actually go back to frame 0, back to the top of the stack, and then it shows us exactly where we are and where the crash happened. If I now try to continue here, it's gonna resume with an error code, but we know that the program actually crashed. The next thing I want to show you are watch points, and they're very useful when you want to monitor how a variable is being accessed throughout the execution of your program. By default, you set a watch point on a variable and it will break the execution. It'll stop when it sees that that variable has been changed. The way these variables are the way these watch points rather are implemented is by having the CPU use a special mechanism that can monitor changes or accesses to a certain memory location. And those are limited in number on your CPU. I'm not going to get into any of the details there because frankly I still need to look into them myself, but essentially that's why this program needs to be running in order to set a watch point. We're not setting a specific line number, which doesn't necessarily change from execution to execution of the program, but because we're telling the CPU to watch a specific memory address, we need to have the program running so that the debugger knows what the address of that variable is, and it can actually set the watch point. So I'll show you what that means in a little more detail. But essentially, you set a watch point on a variable using this command here: watch point set variable, and then the name of your variable. Or you could set how you want to monitor that variable by using -w. So maybe you want to watch just when that variable is read from, or when it's being written to, which is the default, or both, read and write. So let me show you how that works. We've got the debugger here. Now, if I try and set by the way, the shorthand for setting for setting a watch point, instead of typing watch point set variable, you can just do WSV, watch point set variable, and then the variable itself. So if I just try and set a variable, watch point set variable, and say global variable, and the variable that I want to watch is actually this global here that I have in the program. It's just sitting there initialized to 50. Now, normally global variables like this are kind of a bad practice because you don't want to be changing global state of your application from random places in your code. That leads to some silly bugs from time to time. And oftentimes when you run into these kinds of logic errors, it's because you have this global state and maybe your program is so big that you can't really easily track down what's changing this variable. So you just want your debugger to tell you when this variable is being changed. So the best solution here to inspect that is probably a watch point. So let's set a watch point on that variable, right? So the program's now running and it's telling us invalid process. That's because it's not able to actually get any information about this variable, where in memory that variable is. So it can't actually get that memory address so it can tell the CPU, hey, watch when this memory is being accessed, right? In order to know that, we have to actually start the program, halt it, and then we can actually check for that or set up that watch point. So what I'm going to do is actually just set a breakpoint on main. You can set it anywhere before the point of interest in your code. So I'm just going to set it on main right when the program starts. Now I can do WSV global variable, and now it's going to actually, because the program is now running, right? Or sorry, it hasn't actually run it. I need to run it. Now it's running. Now when I do WSV global variable, it can actually figure out where in memory this variable is and actually tell the CPU to watch that memory. So if we hit enter, now we're not getting that error, and we know the variable is at this address, and we have a watch point now. So if I hit continue, what it's going to tell me, because the default behavior is the watch point will trigger when that variable is changed. That's the default. You could also set it, like I said, on read, write, or both, right? But this is the default here. So what it's going to do is it's gonna break as soon as it notices that something is changing that variable. So if I continue, right? Now that this memory has changed, right? It can't stop here at line 47 because it needs to actually know that that memory has changed in order for this watch point to trigger. So what it's done is it's executed that line, that memory has changed, and now the watch point has said, hey, that memory changed, it was written to, so it needs to, it's now going to stop, and it's going to say, okay, look, this line of code here, right before the line that you're currently on, modified this variable. And you could be like, oh, that's why it changed to 75. And you didn't have to actually hunt this down anywhere, right? You didn't have to go through all of your source code and find places that changed that global variable. You actually just set a watch point on that variable and you said, tell me, I want LLDB to tell me when that variable changes. And that's it, right? That's pretty straightforward. Now, let's actually kill that process. And I'll show you, there's also a point in the code here that sets this variable with the contents of this global variable. Now, maybe we want to know, instead of just when it's written to, we want to know when that global variable is actually read from. So let's actually run our program again. So we hit our main breakpoint, the program's running, and we can set a breakpoint. And we're going to set a breakpoint on a global variable. But we want to actually know when it's read from. So let's do that and hit continue. And now we know that this memory is being read from in this assignment here. We're not setting this variable, we're not changing it, but we wanted to know when it's being accessed. So I think you can see how this can be very useful when you're debugging, because sometimes you don't want to go through 30 sources or compilation units, headers, whatever your project is, and actually look for places that are using this global variable. I mean, it's better to not even use global variables all over the place like that, because that leads to very silly bugs. But if you do run into a situation where you want to know that something, where something is being changed from or accessed from, watch points are a great way to do that. The other thing is, if you have a member variable, like for example member var, right? We have this class here that has member var, and we want to see or struct, doesn't matter, it's the same concept either way, but you want to know when this variable is being changed. It's the same syntax, right? It's you have to run your program. So let's run the program again, and now that we're running, right, we can actually get address information. We can say ws, oh, and we can't actually, or can we? I'm not sure. Member var, or is it member? No, member variable. So now if we continue, we can see, yeah, there you go. So that worked. So we set a watch point on this member variable here, and we're able to pause execution whenever that variable changes. And it's going to be the same thing because it gets changed twice, one after the other. It always, like I said, pauses after the actual assignment has happened. And I think you can see how these are useful and how they can help you debug certain parts of your application. The last thing I just want to mention is how to actually kill the process and exit LLDB. There's not much to explain. Kill will essentially just kill the running process if you're at a current breakpoint or something, and you don't want to continue executing the program. Maybe the program is writing to the disk or reading from the network or something. Whatever the case is, you just want to kill the process is all that is. You use the kill command, and then if you want to exit LLDB, you can just type quit or Control D. So if we just quickly go in here, and then let's set a breakpoint on main again, right? Run the program. Now, if I don't want to actually finish executing this program, I mean, I can hit continue and just execute. But if this program is this long running thing, and I don't want to actually like have to run through anything, or maybe it's a GUI, I don't want to switch to the GUI and exit, I can just do kill the program and quit, and that's it. I hope this video was useful. It was meant to be just a quick start guide on making use of LLDB with the command line. Like I said, I know a lot of you probably use debuggers right from inside your IDEs, but if you're like me and you like to know how these tools work just directly, what these tools do, I find you learn quite a bit more about debugging when you actually start playing around with them directly this way. I hope this was useful. Please leave a comment down below. Let me know if there's more I should have mentioned, or if there's something that you were stuck on. I'd love to hear your feedback. And also let me know if you'd want me to dive into any of these topics separately. I'd love to do more videos on this kind of stuff. So let me know what your thoughts are, and I hope to see you again soon.